Hi, this is Guy Eschermann of Noasic, creator of airhdl, and I'd like to give you a short demonstration of how you can use airhdl to quickly generate AXI4 register files for your Amazon F1 custom logic. So I was having a look at the example, at one of the example designs that is available for Amazon F1 in the GitHub repository, and it's called the CL Hello World. And I was browsing through the main source file here for this custom logic module, and I saw that they had custom um, logic or handwritten logic implementing the register file. So you have here different processes which implement the different AXI4 channels, and you can do it in a much nicer way using airhdl. So basically what this does is implement two registers. There is a hello world register, which is at offset 500, and a VLAD register, which is at offset 504. Um, so let's see if we can reproduce that in airhdl. So let's go to the web browser. By the way, airhdl is a web-based register generator, so you don't have to install anything on your PC. You don't have to license anything. You just have to sign up. You can sign up for free, and then you can start using it as much as you like. So I already have an account, so I'll just log in using my account. And the first step will be to create a register map for what we want to do, and I will just call it Hello World. Hello World register map. I could add a description here, and the base address will be 500 hex 500 to reproduce the what's done in the example code, and just create the register map. Here you have the overview of the register map. You can see that the base address is 500. The register width is 32 bits. That's fixed, and you cannot change it. And the revision number here is something that it's an it's an automatic variable that's incremented every time you add a register or you change anything in the register map. This is very useful for checking that the RTL, so for example your system verilog code is comes from the same revision as the C header, for instance. So let's create a new register and call it Hello World. I will also call it Hello World, just like, oh, let's use this capitalization, and the address offset will be 0 from the base address, so it will be 500. And yes, the Hello World register. And this is a register that can be both read and written from the software. And I like to have a value field in it. So registers consist of one or more fields. And in this case, for the Hello World register, I want to have just one single 32-bit field inside that register. So I can use this shortcut. So this is my new register that I've just created. I can have a look at it by clicking on the link, and this is the register description, and you see that it has a value field here that spans the 32 bits. So that's what we wanted. And the other thing, the other register that we want to create is the VLAD register, which is at address offset 4 from the base address, and this is the VLAD register. And this is a read-only register, which means it can only be read from the host, so from the software. And just to show you how you can create fields inside register, I will uncheck this and create the register. So what I now have is an empty register. It doesn't have any fields, and I will create a new field. Yeah, let's call it value, and it will start at offset 0, bit offset 0, and it will have 16 bits. So just create that field. And then I can go back to the register map overview, and I have these two registers in my map. So what I can do now is, if I'm a bit paranoid, I can run design rule checks. So those will check that there are no name collisions between registers, or address collisions, or overlap between fields within one register, stuff like that. You can do it manually anytime, but it will be run automatically before you download any generated files. So what I can do now is download a number of files. So the first file type that you can download is a C header, which contains a number of constants which describe your register map. And I will just open it in an editor, and so you can have a look at it. So these are defined. So you have here the register number for your register map, you have the base address, and you have the offset of every register relative to the base address. And then for every field you have the bit offset and the bit width and bit masks and the reset value. So you can use that in your C driver to access the registers. Also of interest to us is the system Verilog module. So we're going to download that here. System Verilog module. And yeah, it's here actually. It's a system Verilog module. And I will include that into our project. So I will just move it into the design folder. Oh, I had an old one here. I will just delete. This was from my test run. Yeah, and we can have a look inside here. It's well, it's a system Verilog module. It has AXI4 interface, and then for every register field that we have created, we have corresponding ports. So every register, for instance here the hello world register, has a strob port which is pulsed when the register is written from the bus. So this is a control register which can be written and read from the bus, and every time you write something to it, you'll have a pulse on this port. So you can use that in your user logic to detect writes to that logic. And the VLAD register, it's a status register, so it can only be read from the bus, and so the strobe signal is pulsed every time this register is read. So you could connect this strobe signal to resets signal, for instance, if you want to reset some external logic every time the register is read, or you could connect it to read enable from FIFO, for instance, if you want to pop the next value from the FIFO every time you read something from that register. And then we have the data signals. So this is the current data that is written into the value field of the hello world register. So it's 32 bits. And This one here is the value that connects to the VLAD register. So the value that is on this port here, this input port, this is what you will read from the bus. So let's instantiate this register module into our hello world example. So what I will do now is delete this handwritten register file logic and replace it with an instance of the generated register module. So it's called hello world rex, and I want to have a module instantiation. So we have a parameter which sets the AXI address with, and I will just set that to 32 bits. And then it's just a matter of connecting the right ports to the right signals. So it starts with a clock, and then you have the reset, and so on. So I will not do everything here manually. I have prepared a small template that I will just paste here inside. And that's pretty much it. So all these signals here, this is standard AXI for infrastructure signals. And at the end of the port list here, you have the custom ports actually, which correspond to your logic. Yeah, you can then connect them to signals that go to your user logic. So let's just reformat the code so it looks nice. And yeah, that looks nicer, I think, than what we had before. And yeah, this is how easy it is to integrate an airhdl generated register file into an Amazon F1 custom logic. So for more information, if you'd like to try it out, then just visit airhdl.com. And if you'd like to get in touch, you'll find my contact details on the contact page. I'm Guy Eschermann of NoASIC, and yeah, thanks for watching this video.